record. All right. So we stopped here right after our example, and we're going to continue on. And like I said, I want to finish really bad today. So even if it takes the whole period, just bear with me. I know you got to leave. So yeah, that's what I'm saying. Just get up and walk out. I don't think it'll take that long, but just saying. All right. So if it cuts out, make sure you go back in. Same things, same rules as always. Okay. So we can extend our rules for adding random variables to situations involving repeated observations. From the same chance process. For instance, suppose a gambler plays 2 games of roulette. Each time, this should say a $1 bet. There are tons of mistakes in this, and I am so sorry. What can we say about the total gain or loss from playing 2 games? Earlier, we showed that if X equals the amount gained on a single $1 bet on red or black, then remember the mean was a loss of 5 cents. And the standard deviation was actually $1. It is right after we did an example, Pete and Aaron's tours, rules for adding random variables. Okay. Because we're interested in the player's total gain over 2 games, we'll define X1 as the amount he gains from the first game, and X2 as the amount he gains from the second game. Then his total gain, remember we just added them together. So both X1 and X2 have the same probability distribution as X, and therefore the same mean of negative 5 cents and standard deviation of $1. So all it means is that X1 and X2 are exactly the same mean, the same probability for both of them. So if we're looking for the total, we're going to do the mean of X1 plus the mean of X2, which are both the same, negative 5 cents plus negative 5 cents, which gives you negative 10 cents. Because knowing the result of one game tells the player nothing about the result of other games, X1 and X2 are independent. So the variation, I'm sorry, not the variation, the chance did not change of getting the red or the black between games 1 and game 2 because everything was reset. So as a result, we can do that standard deviation by finding the variance. So we do the variance total is the variance of X1 plus the variance of X2. So the variance, remember, is the standard deviation squared plus the standard deviation squared, which gives us $2. So then to actually find the standard deviation of the total, we took the square root of the total variance, which gave us $1.41. All right, so again, it's just adding that, and then remember when you're doing the standard deviation, it's adding the variances and then taking the square root to find the standard deviation. Okay. So X1 plus X2 is not the same thing as 2X. At the beginning of the section, we asked whether a roulette player would be better off placing 2 separate $1 bets, so that's the 1 plus 1, or a single $2 bet on red, which would be the 2X. The player's total gain from two $2 bets on red is that total that we just found. Total equals X1 plus X2. Thus, the sum of random variables has mean. So that mean total was negative 10 cents, and the standard deviation, which we just found, was 1.41. So again, it's just reviewing what we found out. Now think about what happens if the gambler places a $2 bet on red in a single game of roulette. Because the random variable X represents a player's gain from a $1 bet, the random variable Y would equal 2x, represents his gain from a $2 bet. What's the player's expected gain from a single $2 bet on red? So what is the expected y, or the mean of y? The formula said it's 2 times whatever x is, so 2 times the mean of x, which is 2 times the mean was -5 cents, which still gives us a -10 cents. That's the same as his expected gain from playing 2 games of roulette with a $1 bet each time. But look at the standard deviation of the player's gain from a single $2 bet. So we're looking for the standard deviation of y, which would be 2 times the standard deviation of x, which is 2 times 1, or $2. Compare this result to the 1.41 that we just got a second ago. There's more variability in the gain from a single $2 bet than the total gain from 2 $1 bets. So then we're still on this page. There's more to write. Let's take it one step further. Would it be better to place a single $100 bet on red, or to play 100 games and bet $1 each time on red? For the single $100 bet, the mean and standard deviation of the amount gained would be, so the mean would be 100 times the mean of x, or 100 times -5 cents, which will be -$5. The standard deviation would be 100 times the standard deviation of x. So 100 times 1, which is 100. All right. So this is the single $100 bet. Single $100 bet. On the next page, you're going to do the multiple $1 bets. So 100 $1 bets. Is everybody good? So there's that one. So on the next page, for 100 games with a $1 bet, the mean and standard deviation would be like this. So to find the mean, you would have to do the mean of x1 plus the mean of x2 plus the mean of x3, all the way up to 100. So what that means is we're going to add -5 cents plus -5 cents plus -5 cents, all the way up to the 100th time of -5 cents, which would still give you -$5. So the means are staying the same, right? What's going to be the difference? To do this, we have to do the variance to be able to find the standard deviation. So we add the variances. So the variance of x1 plus the variance of x2, all the way up to the variance of the 100th bet, which would be 1 squared plus 1 squared plus 1 squared, all the way till you finished out the 100th 1 square. So 1 squared is 1, added to 1 100 times is 100. But that's the variance. How do we find the standard deviation? Yeah, we're going to square root that 100, which gives us 10. So the player has a much better chance of winning or losing big with a single $100 bet than with 100 separate $1 bets. Of course, the casino accepts thousands of bets each day, so it can count on being fairly close to the expected return of 5 cents per dollar bet. All right, so it's just showing you the mean is going to be the same. You're still going to average -$5, but what's going to come into play is how much you win or lose. So you could either win, $10 compared to, what do we have on the other one, 100, or vice versa. So the bigger the bet, the more you could win or the more you could lose. Okay, so you're taking a bigger risk. All right, check your understanding. A large auto dealership keeps track of sales and lease agreements made during each hour of the day. This problem will come back. Let X equal the number of cars sold and Y equal the number of cars leased during the first hour of business on a randomly selected Friday. Based on previous records, the probability distributions of X and Y are as follows. So we're trying to find the total. Define T equals X plus Y. Assume that X and Y are independent. So it already tells you it's independent, which means what? Why do they tell you it's independent? Why do they let you know? What is the one thing we need? Why do we need to know independence? To calculate what? Standard deviation. So that tells us that we can move on with standard deviation. We don't have to worry about checking whether it's independent or not. So find and interpret the mean of the total. Compute the standard deviation of the total, showing your work. And remember, number one says find and interpret. And then the third one asks us about something else, and we'll come back to that, okay? So let's start with number one. To find the mean of the total, how do we do that? Mean of X plus mean of Y. The mean of X is 1.1. The mean of Y is 0.7, which gives us 1.8. That's only half credit. So if you get this on your test, that would only be half credit. Why? I need to interpret it. Over many Fridays. This dealership sells or leases about 1.8 cars in the first hour of business on average. Any way that you can say that. On average. Sorry, I'm just trying to get it where everything shows up. All right. Number two, it says compute the standard deviation. It's independent, so we can move forward with that. What do we have to do first, though?
Find the variance.
On the variance. So we have to do the variance of the total first, which means the variance of X plus the variance of Y. The standard deviation for X was 0.943, so we have to square that. Standard deviation for Y was 0.64, so we have to square that.
Why are you using the standard deviation and square? Oh, never mind. I get that now.
No worries. Which gives us 1.2988. So then to find the standard deviation of the total, we take the square root of that 1.2988, which gives us 1.14. Somebody interpret that for me. I know it doesn't say it, but interpret it for me. What is standard deviation? So the typical distance from the mean in context of the problem. So the typical distance is about 1.14 cars from the mean on any given Friday in the first hour of business. Okay. All right. Number three, the dealership's manager receives a $500 bonus for each car sold and a $300 for each car leased. Find the mean and standard deviation of the total bonus B. So it tells you what variable to use. So how do we find the bonus? What's our equation for the bonus? How do we get it? How do we get the bonus? Selling and? Yeah, so right here, $500 bonus for each car sold. What represented cars sold? X. What about leased? So give me an equation for that.
Would it be 500x plus 300y?
Mm-hmm. So then how do we find the mean of the bonus?
You would plug in the mean of X and Y.
So 500 mean of X plus, 300 mean of Y. So what's your mean of X?
1.1.
Yep. Plus 300, what's your mean of Y? 0.7. And that gives you a total of 760. So over many Fridays, this dealership sells or leases or earns a bonus on each sale or lease of about $760 on average in the first hour of business. Okay. What about standard deviation? What do we have to do first? Variance. The variance of the bonus. What is different about this equation? What do you have to remember? Not the square root. We'll square root in the very end. But what do we got to do to this equation? So right now it's 500x plus 300y. What do I have to do? I can't just do 500 times
Where the X and Y?
not only the x and y, but what else?
So 500 and 300.
Yes. So that's the big thing. Remember, it's got to be 500 squared times your standard deviation, 943 squared. Then you got to do 300 squared times your 0.64 squared. It'll give you a huge number, 259176.25. And then what do you do to that? What?
Will you like explain what the like? I get that you have to square them, but why do you do that?
Because remember we talked about it. Hold on. Let me find out where we did it the first time so you can see it. Right here when it was a factor. So this was a factor of 22, what does that say? 22,500. So where did that come from? We had to square that 150 that came as well from that bonus. So you always, when you're doing this, everything is squared. Your standard deviation is squared. So make sure that you square your value with your standard deviation as well. So everything has to be square. All right. So then we square root to get our standard deviation, and we get 509.09, which is our standard deviation of our total. So what does that mean? Yeah, you could typically be off $509 from your bonus, give or take. Okay. All right. We're going to flip it over. Now we're going to talk about differences, and differences or subtracts. It's basically the same thing. We're going to subtract, but where it changes is in the variances. Okay. So just pay attention now. Now that we have examined sums of random variables, it's time to investigate the difference of two random variables. Let's start by looking at the difference in the number of passengers that Pete and Aaron have on their tours on a randomly selected day. So to do differences, we're going to subtract x minus y. Because Pete averages, so remember Pete's average passengers was 375 and Aaron's was 310. So the average of y is 3.10. The average distance is, or difference, sorry, is. So that's a little d. Mu of the difference is mu of x minus mu of y, which is 3.75 minus 310, which gives you 0.65 passengers. So what does that mean? Pete averages 0.65 more passengers per day than Aaron does. When we can generalize this result for any two random variables as follows, if d equals x minus y, the mean of d is the mean of x minus the mean of y. So in other words, the mean or the expected value of the difference of two random variables is equal to the difference of their means or their expected values. And again, all they're doing is interchanging those two words. So mean and expected value are the same thing. So for any two random variables, x and y, same thing. If we have a subtraction or a difference equals x minus y, then define the mean of d, which is the expected difference. All you do is the mean of x minus the mean of y. And do remember that the order of subtraction is important, and you guys know that because 2 minus 4 is not the same thing as 4 minus 2. Okay? This should say if we had defined d as y minus x, then the mean of d would be the mean of y minus the mean of x, which in Jeep and Aaron's tours would have given you 310 minus 3.75. In other words, on average, Aaron has 0.65 fewer passengers. How do you get fewer? It's because it's going to come out negative. So earlier we saw that the variance, we just did this, the variance of the sum of two independent random variables is the sum of their variances. Let's return to the Jeep tour scenario. On a randomly selected day, the number of passengers X. On Pete's tour, remember Pete could do 2 through 6, but Aaron could only do 2 through 5. So the difference in the number of passengers is between -3 and 4. So 2 minus 5 would give you the -3, and then 4 would be 6 minus 2. Thus, the range of D is 4 minus -3, or 7. So again, the distance on the number line from -3 to 4 is 7 units. If you guys remember back, what was our range for them added together? So the lowest amount of passengers was 4. The highest amount was 11. 4 to 11 is 7. So their variance should be the same, right? So regardless of whether you have a difference or you have an addition, so sum or difference, your variance or your variation is still 7 for both of them. Okay, so that's what it's trying to tell you. How is this value related to the ranges of X and Y? The range of X is 4 and the range of Y is 3. So the range of D is actually the range of X plus the range of Y. So as with sums of random variables, there's more variability in the values of the difference D than in the values of X or Y alone. This should make sense, just say make sense. Because the variation in X and the variation in Y both contribute to the variation in D. If you follow the process that we did earlier from the random variable t equals x plus y, we were like adding and multiplying and then adding and whatever. You can build the probability distribution of d equals x minus y. So what this little first sentence is saying is I already showed you how to fill in this bottom chart. And you can do that by hand if you want to, but I'm going to go ahead and give it to you, okay? So this is 0.015, 0.055, 0.145, 0.235, 0.260, 0.195, oops, sorry, 0.080, and 0.015. All right, so you can use the probability distribution to confirm that. So you can use this probability distribution to show that the difference in the means is going to be mean of X minus mean of Y. Which was 0.65. You can use it to show that the variance of D is equal to the variance of X plus the variance of Y. So this is the key one right here. For variances, we always add. For standard deviation, we always add. And we've already been through this once, okay? We've already been through this once. So we get 1.1875 plus 0.89 is equal to 2.0775. And then we also know to find the standard deviation, we take the square root of 2.0775, which gives us 1.441. So result 2 shows that, just like with addition, when we subtracted two independent dyslexic right there, independent random variables, variances add. So no matter what, add your variances. And that's exactly what this is going to say right here. For any two independent random variables, X and Y, if you're looking for the difference in X and Y, then the variance of D is the variance of X plus the variance of Y. So regardless, if you're adding or subtracting, variances always add. All right, I'm gonna try to get this one more example in and then we'll come out, we'll go out of this one and go back in. Okay. This is not a lot. So just to remember, we had C, the amount of money that Pete collects, and G, the amount of money Aaron collects. And I'm going to reiterate what those were. So Pete's mean amount of money he collected was $562.50. I'm sorry, 60, $552.60. I was looking at hers for a second. And then his standard deviation was 163.46. Her mean was 542.50. And her standard deviation was 165.03. Calculate the mean and the standard deviation of the difference. And it'll tell you which difference, or it'll tell you within the problem which one you should subtract first, okay? Or which one should go first. So this one wanted D equals C minus G. All right. Interpret each value in context. So the first thing that we want to do is find the mean of D. So how do we do that? Mean of C minus mean of G. Mean of C was 562.60. G was 542.50, which gives you a mean of $20. I did screw this up. It is supposed to be 50. I'm sorry, y'all. Don't hate me. I just rewrote it wrong. Got you. I apologize. So what does that mean? On average, what happens? What did we just do? Not spends, but context the problem. Collects. On average, Pete collects $20 more than Aaron. And it says it right here. Pete and Aaron collect on a randomly chosen day. On a randomly chosen day. Okay. Now we need to do the standard deviation, but we don't do the standard deviation. What do we do? The variance. So we're going to do the variance of D. And we always do what to the variances? So the variance of C plus the variance of G. So we have to square our standard deviations and add them. So 163.46 squared and 165.03 squared, which gives us a big number, 53954.07. To get the standard deviation, sorry, take that square off, the standard deviation of D, I'm going to take the square root of that number, 53954.07, which gives me 232.25. So interpret this. What were we doing? We were doing the difference in amounts collected will vary from the mean by about $232.25 per day. So it could be more, it could be less. They don't know. It just varies. We're going to do the same exact thing. Same exact thing. We're going to go back to the dealership, but we're going to find the difference. I think we can knock this one out really quick. I think we got 3 minutes and 30 seconds. We'll be good. All right, same thing. I'm not even going to read it. It's the dealership one that we just did. Find it and interpret the mean and the standard deviation. And then we have to do the bonuses again, but it's the difference. So how do we do the differences? And I'm not going to ask you to interpret it. So what's the mean of X? Minus the mean of Y is 0.7, which gives us 0.4. To interpret it, over many Fridays, the dealership sells about 0.4 more cars than it leases during the first hour of business. So 0.4 more sold than leased on the given day. All right, so that's number one. Number two, how do we find the standard deviation? What do we have to do first? The variance. So we're going to do 0.943 squared 0.64 squared, and it's going to be the same thing as we found earlier, which was 1.2998. And then to find the standard deviation, we take the square root.
Why didn't you multiply those by the mean that time?
You don't multiply them by the mean. We're not doing the bonus yet. You're thinking about the bonus problem. So then the bonus, it says find the mean and standard deviation of the difference in the manager's bonus for the car sold and leased. So we're going to do the bonus is going to equal 500x, and it wants the difference in the 300y. We're just doing the mean of the bonus, which would be 500 times your mean minus 300 times your y mean, which was 0.7. Which gives you 340. And then the same thing with the standard deviation. You have to find the variances. But remember, because I had the 500 on the equation and the 300, I have to square those as well. So 0.943 squared. We always add, so we're going to add these, and 0.64 squared. We got that same number. We're going to take the big fat square root of this to get that. And it's the same thing as we got just a second ago. And then when it cuts out, come back in. We're almost done, I promise. This next page is easy. All right, I'll see you back in just a minute. Wait, it's the longest minute in my life.